Welcome everyone to the 135th meeting of New Directions in Group Theory and Transit Categories. Our speaker today is Michal Hrbek from the Czech Academy of Sciences in Prague, and he will be talking to us about semi-Bousfield classes over noetherian schemes.
Thank you very much for the invitation to give this talk. So first, a short disclaimer and maybe a semi-apology. Roughly a year ago, my one of my co-authors, Giovanna, gave a talk on essentially the very same topic, but since the year passed and now the project is in a different situation, the paper I hope will appear soon. The project should be nearing its end, so the both the generality and the perspective sort of shifted. So I tried to make the intersections with Giovanna's talk as small as possible, but it's still non-trivial. So if some parts are boring to parts of the audience, I apologize. So nevertheless, this is a joint work with Dolores Hrbek and Giovanna Legros, which again should appear soon. Let me jump into the topic from sort of a different place, not really starting with Bousfield classes or anything similar. So let me start with the story of well, one interpretation of the story of perverse sheaves, or rather coherent perverse sheaves, right? So in these talks, I will mostly be talking about the case of a derived category of a scheme. So X will always be an noetherian scheme. No other assumptions will be needed. And so the perversities, as the story of the story of perversity or perverse sheaves, started in this seminal paper of Bernstein, Bellinson, Delin, and Gaber, which happened in the setting of constructible sheaves. So in this generality, a perversity on the scheme is just an integer-valued function. So perversity is nothing else. The functions do not have a priori to respect any further structure. Once we want to talk about the coherent perverse sheaf story, it's better to actually impose some conditions. And since the scheme is noetherian, all of these conditions can be checked just by looking at immediate specializations. So we have a couple of points. The point y is an immediate specialization of x. So the first condition perversity can enjoy is being monotone. That just means order preserving with respect to the specialization order on x, and of course the usual order on the integers. So that boils down to checking that for each specialization the sort of jump in the value is always non-negative. Then we have the second condition, comonotone. So this ends up being dual to monotone in some sense, but in this maybe less than standard definition, we say that the difference by jumping to the immediate specialization jumps by at most one. And asking that the difference is precisely one, we recover the very classical notion of a codimension function. So let's look at some examples. So the trivial example of a constant perversity happens to be both monotone and comonotone. So this is in some sense the least interesting perversity we can consider. On the other side of the spectrum, we have the, in some sense, most interesting perversity, and that is actually the codimension function. So this function does not exist for every scheme, but it's pretty ubiquitous. A lot of schemes enjoy a codimension function, and if the codimension function exists, then it is essentially unique. So for each on each connected component, two the codimension function can differ at most by an additive constant. And in the presence of a codimension function, we actually have a duality which renders the monotone and comonotone condition dual to each other. So this duality just takes the codimension function and subtracts some given perversity p. And to give some one example which is different, even though I will not really need it. So a dimension perversity, or also maybe we could call it a height perversity. So it's a function that assigns to a point the dimension of the stalk local ring at that point. So this in general can differ from the codimension function. This function is always monotone, but it can fail to be comonotone. So it is always comonotone for Cohen-Macaulay schemes, but outside of that it can fail this property. So what do we buy for considering these perversity functions? Which kind of structures do they govern? So in the story of coherent sheaves, they correspond to some bounded T structures in the bounded derived category. So we consider the bounded derived category of coherent sheaves on X. And here follows this sort of compilation theorem. So this is actually a compilation of of a long chain of results spanning several decades. So in some form, this statement is as follows. So we assume we will need to impose some extra condition on the scheme, which I will for now call nice enough. And if the noetherian scheme is nice enough, then there is an assignment from perversities enjoying these two properties, monotone and comonotone, to bounded T structures in the bounded derived category. And in fact, in the more recent variations of this result, we can promote this to an actual classification. So we can also describe the image. So which kind of perversities are we capturing? And these are precisely the bounded T structures which are tensor, meaning some tensor compatibility condition. I will actually give you the definition of this condition a bit later. Another good news is that this construction is pretty explicit. So one way to describe the T structure is to describe the coil, so the right-hand class of the T structure, the positive part of the T structure with respect to the induced cohomology functor. And this is described in terms of depth. So the coil consists of those coherent complexes whose x depth, so the infimum of the local cohomology with respect to the Zariski closure of the point x, is bounded below by what the perversity prescribes. Yeah, so I should maybe comment a bit about this sequence of references. So this result in the form where nice enough meant the assumption of having a dualizing complex and sort of proving the sort of one way of this assignment. So constructing, given comonotone perversity, constructing the structure. This was apparently known to Delin in the 80s, and it was circulated in some unpublished notes, and later was put into an actual paper by Bezrukavnikov, considerably later. Then in Stanley's paper from 2010, I think this is the first place where this was actually promoted to a classification of this shape. This was in the affine setting under the existence of a dualizing complex. And then the nice enough condition was pushed to its limit by Ryo Takahashi. So he proved that nice enough could be something more general. So not just the assumption of a dualizing complex, which in finite Groove dimension amounts to being a closed subscheme of a Gorenstein scheme, but the CM excellent is enough. So that's effectively being a closed subscheme of a Cohen-Macaulay scheme. And so this was done in the affine setting, and then this Clark, Lang, Manali, Rahul, Parker paper provided the generalization for non-affine schemes. Some kind of nice enough assumption is necessary. So this is a sort of this will not be really the topic of this talk, but I will use the opportunity to mention it. So some assumption has to be made. So there are pathological schemes for which actually these results cannot be expected to hold. So this is a somewhat recent result of me and Lorenzo Martini. So we noticed that at least in the affine situation, but we are finding a counterexample essentially. So for affine finite codimension scheme, which admits a codimension function, so we have the sort of best kind of perversity function, then the CM excellence is actually equivalent for this codimension function to induce a bounded T structure. And there are known examples of affine schemes admitting a codimension function but failing to be CM excellent for various reasons. So there are some limits to where this theorem applies, but of course one has to go to pretty pathological schemes for it to fail. So just to quickly mention, what are these perverse coherent sheaves? These should be the hearts of the induced T structures. So if we denote by HP the heart corresponding to the T structure corresponding to the monotone perversity P, let's look at some examples. So the constant, the least interesting perversity gives us something trivial. So that just corresponds to the standard T structure whose heart recovers the category of coherent sheaves. While the least trivial perversity, the codimension function, its heart is the category which could be called the category of perverse coherent sheaves. And this category is actually not dependent on the choice of the codimension function. So this is the sort of like introduction, this fairly classical story of perverse coherent sheaves. And the question which I want to actually talk about is, what about more general perversities? Do they parameterize some interesting structures in the derived category of coherent or quasi-coherent sheaves? The one way to motivate this is that in the original story of the BBD paper regarding constructible sheaves, no extra assumptions were put onto perversity. So general integer valued functions were considered and were shown to give rise to these structures. And in fact, there are two very well-known classification results which can be described in terms of some more general perversity. So let me explain those. So the first one is still a classification of these structures, but this time in the unbounded derived category of complexes of sheaves with quasi-coherent cohomology, or if the scheme is separated, this is the derived category, unbounded derived category of quasi-coherent sheaves. And there is a sort of small cheat, a small change of notation here. So I said that perversities and in the classical story have been functions which are integer valued, but here it's good to actually allow plus minus infinity to also be possible images of the perversity. So we can assign plus minus infinity to points of the scheme. And then there is the following classification results for these structures in the unbounded derived category. So this is due to Alonso-Jeremías-Saorín in the affine case, and more recently by Dubey and Sahoo in the non-affine case of general noetherian scheme. And this time it's the monotone perversities that classify some interesting class of these structures. So we sort of bend the comonotone assumption. We just consider perversities which preserve the order. And these correspond bijectively to certainty structures. So because we are working in the unbounded derived category, we better have some generalization assumptions. So this is, we are classifying compactly generated structures. And again, there is this tensor condition, which is vacuous in the affine setting, and it's important in the non-affine setting. And the assignment, which is behind this bijection, is essentially the same as in the more classical story. So again, to a perversity, to monotone perversity, we assign a T-structure with a coil, which is described using again the depth invariance. So this assignment is the same, and in fact, this assignment is very compatible with the Delling Bezrukavnikov story. So, in fact, any bounded T-structure in the bounded derived category is a restriction of the corresponding compactly generated T-structure on the unbounded derived category. But note that this time there is no extra assumption on X. There is no nice enough condition. This works for any noetherian scheme. So this is one way how to interpret more general perversities. Monotone perversities correspond to reasonable T-structures in the unbounded derived category. The next result is arguably even more famous. So this is the famous stratification result for a noetherian scheme. And I will I will expose it in slightly non-traditional way, which will fit my narrative, right? So this time, this is the point where the tensor structure enters the picture. And I will describe the stratification in a sort of restricted sense. So it will be stratification of Bousfield classes. So recall that a Bousfield class of an object M is the subcategory which is the kernel of the tensor functor, derived tensor functor on M. So we consider all objects in Dx which are tensor orthogonal to M. And the sort of restricted version of the stratification result can be described as follows. So there is a bijection between perversities. This time there is no assumption on the order preservation, general perversities, perversity functions whose image is only in the infinities, plus minus infinities. And these correspond to Bousfield classes in the derived category. And how does the bijection work? So functions with an image of cardinality 2, they can be interpreted as choice functions, right? So we are choosing some subset of X, and we will take the Bousfield class of all residue fields corresponding to points to which we assign infinity. So of course, this is slightly non-traditional way how to describe a stratification. Usually one just uses subsets of X. Again, it's important to note that the general stratification theorem is more powerful. It actually classifies more general structures which are bounded than Bousfield classes, the localizing ideals. But it happens so that in this setting, every localizing ideal is actually a Bousfield class. This is a non-obvious fact, of course. So the stratification can be described in terms of perversity functions with image in infinities. Okay, so what is the idea? So we have the following diagram. So in the right upper corner, we have the stratification. So Bousfield classes correspond to perversities with values in infinities. Down here, we have the compactly generated tensor T structure who correspond to monotone perversities without any restriction on the image. And underneath that, there is this classical Delin Bezrukavnikov story of bounded T structures in the bounded drive category, so monotone comonotone perversities. But I'm mostly interested about the square, right? And so these two classifications, they have a pullback. So it's clear what the pullback does on the perversity side of things. So we have monotone perversities with functions with the image in plus minus infinity. So we obtain monotone perversities which are infinity valued. So these are choice functions with respect to subsets of the scheme which is closed under specialization. And we know that specialization closed subset of the scheme, they correspond to some particularly nice localizing ideals, which are the smashing localizations, which, because the telescope conjecture holds in this situation, they actually are generated by sets of compacts. So in this way, this is how this inclusion works. So these smashing localization actually are determined by some thick subcategories of compacts. And the question I want to consider is, do we have a push out? So is there some classification result which generalizes both the stratification assignment and the classification of these structures? So can we interpret general perversities without any further assumptions in terms of some natural interesting structures in the derived category of classical hidden sheaves? And this is what I want I want to show you that there is a way how to do that, which how natural is that's upon you to decide. Okay. So now I will actually jump to the abstract general setting of tensor triangulated categories. One reason is that actually like defining the notion of a semi-Bousfield class is as difficult in this setting more or less as it is in the direct category of a scheme. And also I want to sort of foreshadow that we would try to strive for some more general theory at some point. So what is the setting? So we have a rigidly compactly generated tensor triangulated category, which I will just call a TT category or a big TT category. So the derived category of with quasi-coherent cohomology over some noetherian scheme is a special case where the tensor is the derived tensor, the sheaf derived tensor, and the unit object is the structure sheaf, of course. And to be able to talk about positive vanishing or non-vanishing, I need to fix some reasonable T structure on this category. So that's, of course, I'm not trying to fix any terminology here. I just want to cheekily shorten my notation here. I want this extra T to enter the picture. So one T is for triangulated, another T is for tensor, and the third T is for a T structure, right? So I want to consider something I would tentatively call a TTT category. And the T structure should satisfy some basic baseline assumption. So from the point of view of the T structure itself, the triangulated properties, it should be non-degenerate, and it's comfortable to assume it's compactly generated. Actually, something weaker is enough to do basically everything I will tell you, but compactly generated is even more comfortable. And there should be some compatibility with the tensor structure, right? So it's useful to assume that the tensor unit, actually belongs to the aisle of the T structure, so it is non-positive. And the non-positive objects should be closed under tensoring, sort of modeling what happens for the standard T structure in the derived category of modules or of a scheme. And the point is that we have examples. So there are some examples, there are also some non-examples. So the example I will talk mostly about today is the derived category of an noetherian or even more general scheme. This is a TTT category with respect to the standard T structure, the T structure which is induced by the cochain cohomology functor. So the aisle consists of cohomologically non-positive objects and the coil consists of cohomologically positive objects. There are other examples. This is by no means an exhaustive list. So from algebraic topology, we have the stable homotopy category of spectra. This is a TTT category with respect to the Postnikov T structure, defined by the usual homotopy group functor. And there, I want to mention, because I want to sort of go back to this at the very end, very, very briefly. So in the equivariant stable homotopy category of spectra story, maybe if you go to rational coefficients, we also get a TTT category. And there are more examples. What could be a non-example? So usually when one considers a stable module category of a finite group, one should not expect this to be a TTT category because one should not usually expect to have a T structure which is non-degenerate, right? Okay, here comes the main definition of the talk. So what's a semi-Bousfield class? So semi-Bousfield class is should be a generalization of the notion of Bousfield class where we replace the full tensor orthogonality with the notion of the tensor product not vanishing but only vanishing in non-positive degrees. And this is precisely what the T structure allows us to do. So a semi-Bousfield class of an object X is the subcategory, which for now we denote like this. I will comment on that in a bit. So it consists of all objects Y such that the tensor product with X belongs to the coil of the T structure. So it is a positive object. I should mention how this notation was recently sort of suggested or maybe semi-suggested by Paul Balmer to us. I am not sure whether this will end up being the final notation. If you have some suggestions for notation, we will be happy. So for now, I will be using this. So this is the notion of a semi-Bousfield class. For notational, mostly for notational purposes, one can also consider semi-Bousfield classes of whole subcategories defined in the obvious way. And one can actually going by the sort of abstract properties that Bousfield classes enjoy. One can establish most of them with kind of similar proofs, mostly relying on functor category approach. So first, the distinction between semi-Bousfield classes of objects or subcategories is really notational. So for any subcategory, not necessarily an essentially small subcategory, its semi-Bousfield class is the same as a semi-Bousfield class of some suitable object. So this is some sort of compactness that is enjoyed by both Bousfield but also by semi-Bousfield classes. Secondly, the collection of all semi-Bousfield classes in T forms a set, and this set has a natural structure of a complete lattice. So the join operation, again, the idea is the same as for Bousfield lattice. The join of a collection of semi-Bousfield classes is given by the semi-Bousfield class of the coproduct. And there is a natural comparison between the classical Bousfield lattice and this semi-Bousfield lattice, and it's given by a complete lattice embedding. So given a Bousfield class, any Bousfield class is naturally interpreted as a semi-Bousfield class by considering this infinite suspension. This is nothing else than the coproduct of all suspensions in all degrees. And this embeds nicely the Bousfield lattice into a semi-Bousfield lattice. So what we construct is some extension of the Bousfield lattice, which hopefully has some good properties, at least in examples. So this is the notion we want to look at. So from this, the point 3 tells in particular that every Bousfield class is a semi-Bousfield class. What other structures are we generalizing? We are generalizing certain T structures. So a T structure in a TTT category T is called tensor if the aisle is closed under tensoring by objects from the fixed aisle, so by non-positive objects of the TTT category. So this is the condition which appeared in those previous results for T structures with respect to the standard T structure of the derived category of a scheme. And it turns out that there is a nice way how to detect when a semi-Bousfield class fits into a T structure. So it arises from some kind of T structure. So a semi-Bousfield class has some closure properties because it's defined in terms of tensor. So in particular, it is closed under coproducts. And one may wonder when it is closed under products, and that happens precisely when it fits into a T structure as a coil. And then that particular T structure is tensor automatically. And furthermore, we actually capture a whole class of T structures, and those are compactly generated tensor T structures. So the compactly generated tensor T structures, as appeared in the previously mentioned classification, or rather their coils, coincide precisely with the semi-Bousfield classes which are based on subcategories of compact objects. So semi-Bousfield classes of compacts are nothing else than coils of compactly generated tensor T structures in disguise. So again, there is this square which now is manifested in this generality. So we have Bousfield classes in one corner, we have compactly generated tensor T structures or coils of those in this corner. We have the pullback of those which consist of smashing ideals, at least if the telescope conjecture holds. Otherwise, it's compactly generated ideals, right? And now we have like, okay, maybe not necessarily push out yet, but we have this two inclusions into semi-Bousfield classes. So we have this class of structures which generalize both Bousfield classes and the T structures we care about. So this is the sort of proposed kind of structure which maybe is connected to perversities. Okay. So are there any questions at this point? This is maybe a good place to do a brief stop.
Maybe quickly, if you want to make sense of this business for general TT categories, how important is it to have the telescope conjecture, or you would just replace the word smashing by
Yeah, here. So here in this slide, it's mostly for expositional purposes. So when we in our sort of attempt to build some sort of stratification for these semi-Bousfield classes, it seems that it's good to start with TT categories which are stratified. And actually, we at this point we are throwing more assumptions at them. But this is pretty open-ended. I will not be mentioning any results in the direction because this is pretty much a work in progress. So the honest answer is I'm not sure.
Okay, thank you.
Okay, so back to noetherian schemes. So bit of notation. So this gamma xm denotes the local cohomology applied to the stalk of mx. So this gamma xm. What it is the part of m which is supported on the singleton consisting of the point x. And I talked about non-local depth, but in our approach, the local depth plays a role. So what is a local depth of an object of the derived category? So now I'm using this shorthand notation for the derived category of X. This is nothing else than the cohomological infimum of this X piece of M. So this gamma XM, the X local cohomology of the stalk of M. In the commutative algebra viewpoint, this is nothing else than the depth over this local ring at the point X of Mx. And we want to build an assignment from perversities to semi-Bousfield classes. So consider the poset of all perversities. Remember that we allow plus minus infinity as the values. And of course, this is a poset with the order inherited pointwise. And how do we construct a semi-Bousfield class corresponding to some perversity P? So we just sort of mimic what happened for T structures, but we use the local depth because somehow with the local depth, we can at least have an injective assignment. With the non-local depth, it is relatively easy to convince oneself that if we allow non-monotone perversity, we get some degeneracy, and some perversities happen to induce the same subcategory. So to perversity, we assign this phi of P, which will consist of those complexes such that the local depth is bounded below by what the perversity dictates at the point x. And this is a semi-Bousfield class. So alternatively, the description is that this is the semi-Bousfield class of a coproduct over the points. And to each point, we consider as gamma x of the structure sheaf. This is nothing else than the Czech complex at the point x. And we shift it again according to what the perversity dictates. So the image for each perversity is a semi-Bousfield class of something. So we have an assignment, and it is not hard to see that this is order preserving. So we have an order preserving assignment from perversities to the semi-Bousfield lattice. And it has some nice properties. So it is injective just because we can distinguish objects of different depths, essentially. And it recovers the two classifications I mentioned earlier. So if we consider a perversity which is just a choice function, it takes values in plus minus infinity, then our assignment recovers the stratification assignments. Essentially because in the stratification assignment, once the category is actually stratified, we can replace these residue fields. We can replace these residue fields by whatever objects which are supported precisely on a singleton. So in particular, the local cohomologies work as well. On the other hand, if P is monotone, then one can show that it doesn't matter whether we consider the local or non-local depth. So then we recover the classification of compactly generated tensor T structures as well. So we have an assignment from perversities to the semi-Bousfield lattice which does what we want. It recovers the two classifications. So, okay, this is a good candidate, at least from some point of view. But now the question is, okay, what do we actually have? What is the image? Do we hit all semi-Bousfield classes? Do we have some kind of semi-Bousfield class stratification? Or what happens? So that's the next job to explain. And for that, let me come back to the stratification and let me kind of draw some analogy of what we are doing. It will be a loose analogy, to be honest, but hopefully, it will help explain what happens. So how can one frame this stratification? And again, I'm doing stratification just for Bousfield classes. So in the modern viewpoint, of course, in the modern TT geometrical viewpoint, the stratification boils down to two properties. Two desired properties that should be enjoyed by the collection of Bousfield classes. So the first one is the local to global principle, which says that in this case for a Bousfield class, we have the following detection property. So an object belongs to a Bousfield class if and only if all of those gamma x pieces for all points belong to the Bousfield class. So this of course allows to reduce the problem of classification to objects which are supported only on singletons. And this local to global, I will not talk. I will sort of comment on the next slide because the story will be essentially the same in the semi-Bousfield case, fortunately. The second part of stratification which I want to comment here on is minimality. So minimality is in the presence of local to global minimality is precisely what we want for the bijection between subsets of X and Bousfield classes to work. So if the local to global allows us to only talk about stuff supported on a singleton corresponding to some point X, and then we have the whole subcategory gamma xd, which consists of all objects supported on that singleton. This is a Bousfield class, and if the classification works, this should be the only Bousfield class, only non-trivial Bousfield class supported on that singleton. So the minimality, asserts that this is the minimal non-trivial Bousfield class. There are no proper Bousfield subclasses of this, which are supported inside that singleton. Once we have this minimality in the presence of local to global, we have this stratification bijection. And if we restrict to this Bousfield class stratification, this minimality actually follows from something fairly classical and fairly simple. And that is tensor non-vanishing, right? So what is tensor non-vanishing in one way how to talk about that? So it says that if we have two complexes which are both supported on some point X, then their tensor does not vanish. In fact, it is also supported on the same point X. And once we have this tensor non-vanishing, we have minimality for Bousfield classes. Not necessarily for the actual stratification of localizing ideals, but for Bousfield classes, yes, because this tensor non-vanishing tells us there's no non-trivial Bousfield class inside stuff supported on the singleton. And this tensor non-vanishing is easy to prove. So the proof is essentially, the idea is reduced to linear algebra. So we take the residue field at X, we tensor this tensor product, and essentially because this residue field detects the support, and using some usual associativity and so on, one reduces the problem of non-vanishing to linear algebra, where it is a very easy problem. So this is sort of the model which I want to sort of pursue in the semi-Bousfield class situation. So we have two properties, local to global and minimality. So local to global, fortunately, works essentially the same way in the end. So the formulation is easy to state. It's the same things. For a semi-Bousfield class, an object belongs to it if and only if all of the gamma x pieces belong to it. I will just briefly comment on how is this proved for semi-Bousfield classes to some extent to fix some notation. So for semi-Bousfield classes, the direct implication is not entirely trivial. So let me comment briefly. Here it's useful to consider the semi-Bousfield class of the positive objects itself. So what is this? If we sort of unpack the definition, this consists of those objects M such that the tensor product preserves the coil, so the positive objects. So what does it mean for a tensor to preserve positivity? That should correspond to flat dimension 0, right? So more precisely, and this is why the notation is like that, this class f greater or equal to 0, it consists precisely of complexes which are non-negative and homotopy flat. Yes. So in particular, the gamma X part of the structure sheaf, so the Czech complex X, using its usual sort of explicit manifestation, is a complex of flat dimension 0. Therefore, tensoring by it preserves the standard coil, and that amounts to computing the gamma X cohomology. So this is why we have the direct implication. For the converse implication, so one should try to carefully describe how an arbitrary object of the derived category deconstructs into the gamma X pieces. So for the usual stratification, to deconstruct, it is enough to just consider localizing ideal generated by the gamma X pieces. In our case, we have to be slightly more careful, but fortunately, this is essentially available in the literature. So it turns out that every object can be deconstructed to gamma X pieces just using extensions and coproducts, essentially. And semi-Bousfield classes enjoy these closure properties, so we are fine. This slide can be reasonably generalized to TT categories with relatively natural assumptions. We don't have probably the best formulation yet, but this seems very doable. Okay, what is more tricky is the minimality. What is the minimality that we have sort of considered? Minimality in quotation mark, because there is no real minimality around here. The problem of like setting up some kind of stratification manifests already in this T-structure classification. What actually is minimality when we allow only one-sided shift, right? So here, a bit of notation. So this gamma X d bigger or equal to n, so that just those objects supported on a singleton X which live in cohomological degrees from n and beyond. And the minimality condition here in quotation marks is the precise condition that allows us to prove that some semi-Bousfield class is fully determined by a perversity function. So for a semi-Bousfield class of some object, we say it is minimal if, because we have local to global, it is some local condition with respect to a point. So the condition says that if an object supported on a singleton X falls inside the semi-Bousfield class, then it takes into the semi-Bousfield class every another object which is supported only on X and lives in the same cohomological degrees with respect to the positive side. So this is almost tautologically constructed in a way that if this condition holds, we show that the behavior, the objects which belong to the semi-Bousfield class supported inside X, they depend only on a single parameter, which is an integer or plus minus infinity. It all depends only on the cohomological bound. So, okay, this is a condition which we want to study, and now we would like to translate it somehow. We would again like to reduce to linear algebra to allow us to actually show that this minimality holds in the derived category of a noetherian scheme. The problem is we cannot really use tensoring by the residue field this time because we are checking positivity with respect to cohomologies, and of course tensoring tends to sort of introduce negative degrees, right? The idea comes from this body of papers on classification of these structures, varieties in commutative algebra or other schemes. The success came from applying the sort of dual construction. So applying the internal home, the derived home from the residue field. So in some sense computing not the derived top, but computing the derived socle, if you will. And this of course has a high chance of success. So our semi-Bousfield classes are closed under co-suspensions. So this, at least formally, it goes in the right direction. And in fact, we have the following lemma. So for a semi-Bousfield class, the following are equivalent. So the condition one is the one we are interested in. We are trying to characterize which semi-Bousfield classes arise from perversities, so they are in the image of our assignment. This is equivalent to minimality. This is close to being a tautology in the end, in the presence of local to global. But namely, there's the condition 3. So this is the reduction to linear algebra, essentially. So the condition is that whenever we find an object in the semi-Bousfield class, again supported on a singleton X, then also if we apply this derived socle on the residue field on X, it still belongs to the same semi-Bousfield class. So here, this is where the story sort of starts to take some shape. So what is the technical difficulty? So to check that our structure is closed under this R-homing, when one starts to sort of try to do some devisage argument, it quickly becomes apparent that products would be nice. If our semi-Bousfield class is closed under products, then one can show this condition 3 just holds. But of course, this is the T-structure setting, and we would like to do something more general. Fortunately, there is another case where this condition 3 is easy to show. So if we assume that our situation is homologically simple, so what if we assume that the scheme is regular, right? Or the stalk is regular? Then this residue field becomes compact, at least locally. And then this last condition is easy to prove because once we have compactness, compactness is equivalent for the residue field to be dualizable. And then you use the usual yoga of dualizability trick. So we sort of make the internal homes and tensors commute and everything sort of aligns. So this leads me to the first result. So this is the sort of actual kind of stratification which we are able to show in the regular case. So if the noetherian scheme is regular, then our assignment is actually onto the semi-Bousfield lattice. And in this case, we have a really nice isomorphism of complete lattices between perversities, the general perversities, and all semi-Bousfield classes. So this is like the best possible situation. The bad news is that this situation actually characterizes regular schemes. So we can prove this for regular scheme, and we know that whenever we have singularities, this fails. Why is that the case? I can quickly explain that because that's fairly naive thing to do. So what if we have a singularity at some point? So we have a singular local ring. Then it turns out that it's the semi-Bousfield class of the residue field at that point which fails to be determined by a perversity function, right? Why is the case? So singularity amounts to the tensor power of the residue field actually not being cohomologically bounded from below. So we have infinitely many negative cohomologies. And this has an immediate interpretation with respect to the semi-Bousfield class. This means that there is no suspension or co-suspension of the residue field that would belong to its own semi-Bousfield class. On the other hand, if we consider another object which is supported on the singleton, namely the Czech complex, the local cohomology, because tensoring by it acts as an identity on K, it's easy to see that there is a co-suspension by one, which actually belongs to the semi-Bousfield class. So we have two objects which are both supported on the singleton, and with the same cohomological infimum, and one belongs to the semi-Bousfield class and the other doesn't. So the minimality fails here. The observation is, of course, what is the difference between the two objects? One has finite order dimension, the other doesn't. So maybe that's the idea how to describe the image of the assignment. So that's the next step. So in the singular case, we know that the assignment is not onto the semi-Bousfield lattice, but maybe we can describe the image, and in fact we can. So that amounts to sort of analyzing some kind of non-vanishing. And it turns out that it works sort of narrowly in a way that we require in order for the classification to go through. So a bit of notation. So F plus will denote the subcategory of all complexes of finite or dimension. So this is simply put, these are homotopy flat bounded below complexes. And we will now consider a sublattice of the semi-Bousfield lattice. So consisting of those semi-Bousfield class of objects of finite or dimensions, and we can allow also subcategories of objects of finite or dimension. So this is the sort of narrow version of tensor non-vanishing, or rather maybe internal home non-vanishing that we use here. So how does it work? We consider a general complex M, and we consider F, which is of finite or dimension, and it is actually local with respect to some point. Then we have the following equality of cohomological infima. So what do we have? We have two R-homes, which more or less compute the interaction of the R-home from K, so the derived socle, with respect to the semi-Bousfield class, right? So if we define a semi-Bousfield class of F, then we care about this tensor. This tensor, non-positivity of this tensor decides whether M belongs or does not belong to the semi-Bousfield class. And by some commutative algebra results, applying the derived socle does not change the infimum. And on the other side, so the condition of minimality we have extracted ask for this derived socle of M to also belong to the semi-Bousfield class, which is decided by positivity of tensoring by F. So this is what we want for the minimality to go through. And I will only remark, so why this trench formulation, what actually happens here. So there are some cases, so in most of the cases, this equality of infima actually follows from some isomorphisms of complexes, right? So the first remark, that's the regular case, which I will, okay, so what we actually do in the regular case. So if K is compact, then I mentioned that we somehow dedualize using dualizable property of K. This is the isomorphism we get, right? So we can sort of switch between, we can simply put this R-hom and this tensor commutes by, this follows from the fact that K is compact or dualizable. So in this situation, we have this isomorphism, which of course trivially provides this equality of cohomological infima. And in fact, this isomorphism holds more generally. And this is still fairly classical. So in case F is of finite or dimension and M is cohomologically bounded from below, then the same isomorphism still holds. So this is Avramov and Fox-Bis, at least the first reference I know about. So this time this does not really follow from some dualizability, but from some devisage argument. So why this formulation does not use an isomorphism? This is because of the last case. So the general case where M is in general does not satisfy any cohomological bound. One can see via examples that in this most general situation, the isomorphism between the two complexes can never hold. So this actually fails somewhat horribly in the singular situation. But somehow, luckily, this equality of cohomological infima still holds. So this is what we prove. This is essentially the commutative algebra burden of our proof that we needed to go through, and luckily this worked. So this is some impromptu argument with cochain complexes we had to do. Yeah, so there is some version, morally speaking, we have some version of non-vanishing of tensor or internal home that is behind our minimality when restricted to finite or dimension. What is the result? So for a noetherian scheme, now allowing singularities, our assignment yields a lattice isomorphism between general perversities and semi-Bousfield lattice restricted to objects of finite or dimension. So coming back to the picture, that's the class of structures that one could put into this push-out square, which is classified by these general perversities and generalizes both the Bousfield class stratification and the classification of compactly generated tensor T structures. So again, to reiterate, in case the scheme is actually regular, you can just put semi-Bousfield classes here without any further assumption. It becomes a bit nicer. Okay. I think I could make a second stop here before going to the last part, which is some, let's say, applications. Are there any questions? Okay, if that's not the case, then I have last sort of two small points. It's essentially like an application and a special case. So, okay, I have sort of explained how stratification, albeit restricted to Bousfield class case, fits into this. How do the T structure classification fit into this? So the good news is that one can actually recover the classification of compactly generated T structures out of this classification of semi-Bousfield classes. And the way to recover them is fairly cheap. So this gives us some hope that maybe this could be sort of a top-down approach to T structure classification in some other TT categorical settings. So I will just very briefly comment on that. So the main point is this lemma. So given a perversity on our scheme, the following are equivalent. So the perversity being monotone, which is the property which we expect to correspond to some T structure, can be actually proved fairly directly to be equivalent to the semi-Bousfield class in the image to be product closed. And this we have seen in more generality means that the semi-Bousfield class fits into a T structure as a coil. And the proof of this is fairly direct. So one implication I've already mentioned that can be made more abstract. The other implication is some real direct computation over the scheme. And the only thing that remains to show after this fairly cheap step is just to show that the T structures in the image are compactly generated. And this can be done using some fairly standard arguments over the scheme. This is not so abstract, but in the case of this of a scheme, we can do that. So this is, yeah, what I mean to say here is that to get the structure classification out of the semi-Bousfield classification is maybe half page. So that's one thing. Another thing is maybe to illustrate, so what kind of structures do we get? So some special semi-Bousfield classes can actually be read directly from the category of quasi-coherent sheaves. So this is a perspective which is maybe module theoretic or commutative algebra theoretic perspective. So this is a definition which I think is rather niche, but it's sort of popular in my hometown. A pair of subcategories of quasi-coherent sheaves, so we are in the Grothendieck category of quasi-coherent sheaves, is called the hereditary Tor pair. If these two subcategories are maximal with respect to an orthogonality condition, and the orthogonality is that with respect to these Tor functors, so nothing else than the higher derived functors of the sheaf tensor product. And it turns out that these hereditary Tor pairs are can be easily interpreted as special kind of semi-Bousfield classes. So two hereditary Tor pair, these are sort of symmetric, so we choose which of the two classes we want to care about. How do we get a semi-Bousfield class in the derived category? We just extend by sort of tensor trivial objects, which will be objects of flat dimension 0 or 1, actually fits the narrative. So this should be, if you know the notion of a Happle-Wright and Smallot structure, this is something similar. So in the derived category of an abelian category, there's an assignment from torsion pairs in the abelian category to T structures by extending them by sort of the standard IL and coil. And this is something similar. So the hereditary Tor pairs could be viewed as sort of Happle-Wright and Smallot case of semi-Bousfield classes, if that makes any sense. And the whole classification restricts in relatively nice way. So it's better here to assume X is semi-separated. And then, so we have this classification of these hereditary Tor pairs. So on the level of semi-Bousfield classes, we had this restriction on the Tor dimension being finite, which is reflected here. And these correspond to perversities satisfying this bound. So for each point, the value of the perversity is non-negative and bounded from above by the local depth at the point. So recall here that this depth function itself is a perversity. And it can fail to be monotone, right? So in case the scheme is not Cohen-Macaulay, this function itself can be an example of a non-monotone perversity, which actually gives rise to some hereditary Tor pair, which in turn corresponds to some semi-Bousfield class. And again, in the regular case, we just characterize all hereditary Tor pairs this way, again. So this is a piece of the work which actually is available at this point, at least for affine schemes on arXiv, and this is somehow where we started. So this arXiv submission has the same set of authors as this talk. Yeah, no, I can just mention that this actually gives a partial, but I would say substantial answer to an open question in this book. So this book has been very important to me, not only because it is co-authored by my PhD advisor, and this book is full of questions. Many of them are still open, and one of those questions was characterized Tor pairs over commutative noetherian rings or affine noetherian schemes. So we were happy that this sort of direction gave a partial answer to that. Okay, I'm almost done. I have one last slide where I want to sort of discuss where we plan to continue with this. So there are sort of 2 points. The first one, so there is a qualitative difference between the classical Bousfield lattice and our semi-Bousfield lattice in the case of a scheme, right? So the Bousfield lattice is completely oblivious to singularities because it is just lattice isomorphic to subsets of X. So it's actually even oblivious to the topology on X. But the semi-Bousfield lattice is somewhat sensitive to singularities, right? We have seen that the assignment hits all semi-Bousfield classes if and only if the scheme is regular. And we wonder how much this semi-Bousfield lattice actually knows about the singularity category. Can we extract some kind of information about it? So we're trying to work on that, and the problem is actually computing examples. So far it proved difficult to compute even pretty small singularity, to compute the semi-Bousfield lattice fully for even for even small singularities. So that's what we are trying to pursue. And the second point, okay, this was sort of intrinsically present in the slide. So we think this should be generalizable. So we are pretty certain that there are other examples where this story unravels in a similar way. So it seems that, for example, commutative noetherian DG algebras or the rational equivalent stable homotopy theory, let's say of a finite or discrete group, seems doable, meaning that we should have, again, this stratification assignment, which either should be onto the semi-Bousfield lattice or maybe depending on singularities and so on. The question is there some more general nice theory behind, and that's what we are trying to do. So maybe I will be able to again talk about that in a year or two. Okay, so with that, I think I'm done. Thank you for your attention.
Thank you, Michal. Can we all give the speaker a round of applause, please? Okay, if you have any questions, please ask them.
Sometimes, may I ask something? Sometimes it helps to have just to name things. So, could you, for a general triple T category, big T T T T T T T, stop at that. Can you express what type of classification you would expect? Maybe, I mean, from the T structure side to perversity functions or backwards? I guess backwards is a bit tricky. You have to construct them, but maybe to get an invariant in functions on the spectrum might be something you could do, no? And then say, okay, we say that the triple T has a stratification of T structure. I mean, you need adjectives, but T structures with some properties. If this holds, and then just at least we have a question, and then we can say, okay, this new class of triple T categories does the classification on. Have you reached this level of formulation?
So the annoying thing is that this distinction between regular and singular case, because in general, so one thing is that one can, in the reasonable TT categorical generality, one can model again this class of objects of finite flat or third dimension. And modeling it on the scheme result, one can take this as the subcategory on which we want to do the classification. So one could consider the general assignment from perversities to the semi-Bousfield lattice, and under, I would say, relatively okay assumptions, maybe not like the best assumptions, but we have some set of assumptions which allows to show that this is injective into the semi-Bousfield lattice of objects of finite flat dimension, and then one can formulate this stratification as this being surjective. So there is a formulation, but yeah, we have not achieved anything which we would really consider super aesthetically pleasing at this point. So, for example, one assumption which lifted a lot of weight for us was assuming that the localizations at the points, so mimicking the localization at the prime ideal, are T-exact. And the problem is that we don't have that many examples. I think this can be extracted from literature, from the rational stable homotopy theory of discrete group. So that's why I also
Okay.
mentioned that case.
Yeah, it was the second question I was going to ask, maybe more philosophically about localization at point. If we think of the stable homotopy category, right, in topology, you have a global T structure or you have it P locally, but you probably don't have it at various heights, right? Because you create periodicity and so I guess localization is a bit of an issue when you, I don't know, or you create degeneration or something, I don't know.
Yes. Also the case of the spectrum not being noetherian, we also really don't know what to do there. So for now we really started with the stratified situation.
Thank you. It's exciting, interesting.
Yeah, we also, as another thing, we really don't know how to include co-stratification into the picture.
Thank you. Thank you for the talk.
Thank you, Michal. Thank you, Paul. Any other questions? And can you click on minus again on the video?
Yeah, sorry.
Okay.
Maybe if I do it like that, just, yeah, okay.
No, a minus would be better because
Mine is
otherwise
better. Okay.
we will appear twice on the record. Any other questions? Anybody? So going back to the part where you said that your result regarding hereditary torsion pairs on QCO of X answered partially answered a question of Gobert and Purify. So hereditary torque pair, sorry, on QCO of X. So why do you say partially? Because of the hereditary adjective?
It, so a priori, the question asks about all torpors. So there are like
Okay.
2 degrees of generality. So even in the regular case, we do not hit all of them because we have this hereditary condition. So torpor in general is orthogonal just with respect to the first derived functor of the tensor. But that's maybe taking into account all higher torus is natural. But then the singular situation where we only classify those hereditary torus pairs which are generated by objects of finite flat dimension.
And staying on this theorem, can you just maybe say how X being semi-separated helps you in the proof? I mean, is that a very crucial? I'm guessing that's a very, I don't know, needed type of
I
proof.
think it's probably not crucial here. So here, for me, it's more natural when talking about quasi-coherent sheaves to really consider resolutions by flat quasi-coherent sheaves, and for that you need semi-separated. Actually, you need that in sort of sharp way. There's a paper by Jan Šťovíček and Alexander Slavik where they sort of prove the converse to Morphet theorem. So you have enough flats if and only if the scheme is actually semi-separated.
Okay. Okay.
But probably you can formulate this by using flat resolutions in the ambient category of sheaves. And probably, I'm pretty sure there is some formulation that does not need that, but yeah.
Well, any other questions? Anybody? And sorry, you mentioned in your answer to one of Paul's questions probably that you're not yet sure as to how co-stratification might fit into the picture. So when you say co-stratification, are we also supposed to be thinking of weight structures as opposed to T structures?
That's one part of story I did not include. So some T structures, or the certain T structures are special cases of semi-Bousfield classes in this way, right? And this is a sort of next step. So on the other hand, each semi-Bousfield class actually fits into a weight structure. So in fact, semi-Bousfield classes correspond bijectively to those weight structures which are co-generated by Brown-Komenets duals. So you have this immediate sort of connection to weight structures. So that's sort of one way. But if you then talk about more general weight structures, it's not clear to us how to, for example, how to have a story um, which would involve co-stratification in the sense that it's not clear to me. Yeah, but one should probably not do co-stratification of all colocalizing co-ideals, but sort of like the Bousfield version. So maybe like right orthogonals with respect to the internal home, maybe would be um, one class of structures with which one would try to sort of make like a once to make to construct a version which only takes into account
Yeah,
vanishing in only in one direction, right? And yeah, so that's not clear to us how to do that essentially.
yeah, I think this is the version of co-stratification that was looked into in that paper by Leo, Anna, and I think Eduardo something. But yeah. For
Yeah,
DTs,
yeah, yeah.
we know we have the post-certification result anyway. Yeah. But in this gen, yeah.
Yes, kind of trying to like construct a similar diagram as here, but having co-stratification there, or maybe again some restricted version of co-stratification with respect to the internal home.
Okay. Any other questions? Sorry, this theorem on the screen here, it fails without the noetherian assumption.
Sorry, you asked whether it needed noetherian assumption.
I'm asking if it fails without the I'm asking if it fails without the noetherian assumption.
So without noetherian assumptions, even the things like stratification or telescope conjecture can
Yes,
fail, and this would
yes,
sort of
yes,
also have ramification for this.
yes.
Um, but for example, whether we can, yeah, this is certainly not the optimal generality because there are many non-Noetherian schemes which satisfy either stratification or telescope conjecture. Yeah, we have not tried to really think about it.
Yeah. Mhm. Yeah, there was an example by Keller in the affine case, I think.
Yes, yes,
Yeah.
yes. Yes, certainly there are also cases of interest where where this could be studied, where telescope conjecture fails, like valuation domains, where a lot of information has been gathered about localization theory and the smashing spectrum and things like that. But yeah, we have not tried yet.
Okay. Thank you. Any more questions? Anybody? If not, let's thank Michal once again. Okay, thank you all for coming. We have Julia Schneider from Burgundy speaking next week. Bye bye.